Okay, I started the recording. Okay, so uh, today we are going to discuss the remaining topics of week 10. Okay, and after that, we will solve some questions on that, and like it will be some mixed question from week 9 in week 10. Okay, so first let's go through the topic that we were left in the last session of our week 10. In the last session, we have covered the gradient descent part and our parametric equations. Okay, so first topic for today classes would be tangent line equation, or you can say plane and hyperplane equation. Okay, so if we have given any function z equal to f of x comma y, okay, first we are considering the case for two variable where we have only two variable x and y. So for that case, the tangent line equation at the point x naught comma y naught would be given by this formula that we can say f of x naught comma y naught. That means what would be the value of my function at the point plus fx at x naught comma y naught. Find the partial derivative with respect to x at this point. Take the dot product with x minus x naught and plus same thing do with the second variable y. Okay, this same formula we can actually convert it for our multivariable case also to find our tangent plane and hyperplane. See here, as we have only two variable, okay, so the dimension you will get for this line, okay, this will be have a dimension 1, which we know is a line. Okay, while when we have more than two variable, in that case we will get plane, and as we go along in like 4 dimension or greater, then it will be in hyperplane. Okay, anything above 3 dimension we call it as a hyperplane. Okay, because we cannot imagine beyond 3 dimensional space, so we just name them as a hyperplane equation. So for any function f x tilde basically the group of the vector x1 comma x2 comma till x10. Okay, on domain D and R. Okay, now suppose the gradient of f exists at that point. We want to find my tangent equation at the point a tilde. So for finding tangent plane or equation or line, hyperplane equation, anything, evaluate the function value plus these both basically are the same thing, because in the first I have written gradient of f at the point a tilde dot product with x tilde minus a tilde. That means here what we are doing, that basically here it is the same. Okay, like first uh, partial derivative of the function with the first variable at the point whatever the point given to you on which you are finding tangent, take the dot product with x minus first coordinate of the point, same do with the second variable, and this will continue. Okay, so let's solve one question to grasp with this concept. Okay, so we have given the function f of x comma y as under root of r square minus x square minus y square. Okay, now we need to find the tangent at this point. Okay, so first understand that as we have the function of two variable. Okay, so basically you need to find the tangent at the point 0 comma 0. The third value that is given r is basically the value of my function f at the point 0 comma 0. Okay, so this r is basically nothing but f of 0 comma 0, that you can even try by putting 0 comma 0 in the function f also. Okay, so according to my formula for tangent equation, at any point if I want to find the tangent, I will first find the function value plus gradient of f at that point, whatever the point given, and multiply with the x tilde minus a tilde. So I have found the function value, that is r. Now turn for the gradient. So gradient is basically fx and fy, partial derivative with respect to x and partial derivative with respect to y. So for partial derivative with respect to x, my function given is this r square minus x square minus y square. Now if I want to find the partial derivative with respect to x, what would be the partial derivative for this function? Can anybody tell me? Partial derivative with respect to x.
Uh,
So,
2x by
okay, 2x by
no by root r square minus x square minus y square, and yeah,
uh, it's a little bit wrong.
Minus 2x by the same thing.
Uh, it's just that that 2 will not come. Okay, and now because what in the starting when we started the partial derivative, I told the trick how to find the partial derivative for this type of function. As this is a composite function, okay, we have one outer function that is taking the square root, and we have one inner function that is r square minus x square minus y square. So I will consider this as a under root of, let's say, capital X. Okay, where what is my x? X is simply this the inside function that is r square minus x square minus y square. So if I just want to only find the uh, partial derivative or derivative of this under root x, this is basically x power 1 by 2. So to find the derivative, what would be 1 by 2 times half minus 1 is negative half. So it will go in the denominator, that is under root x. Okay. And we assume that my x is this function here. So I will just replace this with r square minus x square minus y square. Now we need to multiply this with the derivative of inside function. That would be negative 2x. Okay. But these 2 and 2 will cancel out. So we will only remain with this. Okay. You were correct by this point, but it's just that this 2 will also be cancelled out with this 2. Okay. The half, as we will go in the front of while we will taking the partial derivative. Okay. So that's because this 2 will cancel out and we will only left with this term. Got it?
yes sir.
Yeah. And the same would be for the case for y. It's just that it will be negative y divided by r square minus x square minus y square. Okay. So now gradient of f x comma y was negative x upon under root r square minus x square minus y square comma negative y upon under root r square minus x square minus y square. Okay. But basically what we need to do, we need to find my gradient at the given point. Okay. So the point that was given to me was 0 comma 0. So if I want to find my gradient of f at 0 comma 0, it would be just simply 0 comma 0 because 0 in the numerator in both the terms. So it would be just 0 comma 0. Okay. So my tangent plane equation was f at 8 till plus gradient of f at 8 till times x till minus 8 till. This was my r. Okay. This I have found was 0 comma 0. Okay. And this will take place the dot product with x tilde minus 8 tilde. So that is basically 0 comma 0 dot product with x minus 0 plus 0 comma 0 dot product with y minus 0. Okay. So if you are going to do this, you will just simply get z is equal to r because everything here will be just 0. Okay. Or either you can go by this or you can write it this also, that is xi minus ai. Okay, that was the second form. Okay, this was the first form, second form was the this one. Okay, these were the same. So this was again r gradient, oh sorry, partial derivative with respect to first variable x was 0 at the point my 0 comma 0 multiplied with x minus 0, plus again partial derivative with respect to y at 0 comma 0 was again 0 and y minus 0. Okay, so z is equal to r. Any doubt in this question?
Sir, can you please scroll up a bit?
Yeah.
Sir, this first explanation of solving this z. Sir, can you please explain this part once again? This.
Okay. This was z is equal to function value at the point a tilde plus gradient of f at the point a tilde dot product with x tilde minus a tilde. Okay. This here expression and this expression is basically the same. Okay.
Oh, okay.
So, so either you can go by this or this. That is just to take the whatever first find the partial derivative with respect to x. It comes out at 0 at the point 0 comma 0. Multiply that with x minus the point. That is the x coordinate of the point on which we are finding the tangent. That is 0 here. Okay. Then y here was the partial derivative. This 0 here. This 0. Okay, was the partial derivative with respect to y at the point 0 comma 0. Okay, while this 0 was the point
Oh,
0.
yes.
Okay,
Okay, sir.
okay, the outer this is the partial derivative, this inside 0 was the point 0 on which you are finding. If you were finding at the point 1 comma 1, then here it would come as x minus 1 and y minus 1, and here also the partial derivative comes with at the point 1 comma 1. Okay, so we have one more question. Find the equation of the tangent plane to the graph of the function given by f of x comma y is equal to 1 by root c multiplied with under root of b minus ax square minus by square at the point 1 comma 2 comma f of 1 comma 2. As I told, when we have two variable and if it is asking to find the tangent plane, okay, the third component that will be given was the value of the function at the point 1 comma 2. If we have three variable and the vector belongs to R4, then the first three would be the point on which we are finding tangent. The fourth component of that vector would be the value of the function. Okay. So here basically my point x naught comma y naught is 1 comma 2. Okay. So I need to find first my value of function at the point 1 comma 2. Okay. So just simply plug in x equal to 1 and y equal to 2 in this. I will get 1 by root c under root t minus a minus 4b. Okay. Just putting x equal to 1 and y equal to 2. I got this. Now the next thing is finding the partial derivative. Okay. Fx and fy. So partial derivative with respect to x. Okay. Now we just so in the before question we also dealt with the same expression. Okay, it's just that one constant 1 by root c is getting multiplied. Okay, so in the derivative that we also got, it will be it would be just the same. Okay, except that this constant is also getting multiplied with the our final result. Okay, so what was the partial derivative that we got?
Sir,
Yes.
uh, that is written at the point 1 comma 2
Yep.
comma function
Yeah.
of 1 and 2. What is means, sir?
uh, Actually this is written at like that because this 1 comma 2, that is the see here there are two variable. Okay, so the first
Hmm.
component of that point would be basically your point on which you are finding. Okay, third would be the value of the
Okay.
function at that point. Okay, now if we I have the function, let's say x comma y comma z, then it would be you will be asked to find, let's say 1 comma 2 comma 3 f of 1 comma 2 comma 3. Okay, so you need to basically find the tangent plane at the point 1 comma 2 comma 3. The fourth component would be the function value. Okay, at that.
Okay.
Now,
Yes, sir. Sir,
yes, yeah,
sir, sir, can you tell me how this came? 1 by root C root over D
yeah. Okay,
minus
okay.
A.
Okay, my function is given as 1 by root c times under root of d minus ax square minus by square. Okay, if you just put x equal to 1 and y equal to 2, because at this point we are finding the tangent line. Okay, so we need to plug in these values x equal to 1 and y equal to 2 in this expression. So if you put x equal to 1, x square, that is 1 square 1, that would be just a, y equal to 2, that is 2 square 4, so it would be negative 4b. So the function value at the point 1 comma 2 would be 1 by root c time under root of d minus a minus 4b. Okay, got it?
Yes,
Yeah. Okay, so we found the function value. Now derivative. So first find the partial derivative with respect to x. We already dealt with this expression, so I will just quickly write this: minus ax upon under root of d minus x square square minus dy square. Okay, and 1 by root c, because it's the constant, so it will be the same. Okay, so basically this is just this. Okay, root c times under root of d minus x square minus by square. Okay, uh, now if I write fy, it would be just minus by divided by again under root c under root d minus x square minus by square. Okay, so the point on which we are finding tangent is 1 comma 2, so we need to basically find the derivative at that point only. So fx at 1 comma 2 would be what? Minus a upon under root c under root d minus a minus 4b. Same fy at 1 comma 2 would be minus 2b divided by under root c d minus a minus 4b. Okay, uh, okay, just let's write t equal to under root c t minus a minus 4b. Okay, let's suppose
hello, sir.
t, yes, yeah,
Sir, can you tell me, sir, how this derivative came, sir? F of y that f of x.
okay. See, in the previous question we have this expression for finding partial derivative, right? And also the next question we have the same. Okay, it's just that there are some constant that are multiplying with the x term and y term, and there's one constant term also, that is 1 by root c. Okay, so how we find the derivative for this function? We consider that the inside expression r square minus x square minus y square to be one capital X. Okay, so now my function become under root of capital X. So if I find the derivative of root x, that is simply just the x power 1 by 2, it would be 1 by 2 times under root of x, because half minus 1 would give me negative half. Okay, so negative power it will go in denominator, so it will be 1 by 2 times under root of x, and then I just put the value of x that I suppose that is r square minus x square minus y square here. Okay, so I have found the derivative of outside function. Now I need to multiply this with the derivative of inside function, that is negative 2x here. Okay, so this 2 and this 2 will cancel out. I will left with this part. Okay, as this derivative was clear?
Excuse me, sir. In the
Yes.
question that you were solving, there is 1 by root c. So how will you take that x in under root in that question, sir, to solve this
Uh,
outer and
this
inside?
we will just consider one constant. Okay, so this
Okay.
will the change will not happen, right?
Yes, sir.
This will be constant for the whole time in the derivative. Derivative is rate of change of the function. Okay, so only the variable thing will change. This is the constant, so it will just be there. Okay.
Okay, sir.
Okay. So here in this we found the derivative like this. Okay. In my next question it was just ax square. So the a will also come here and 1 by root c is also there in that. So these two are basically constant. So these two will remain at their places. Okay.
Yes,
Is it
sir.
clear now? So now what I have done here, this expression, okay, under root of c times under root of d minus a minus 4b, I am considering this as a t. Okay, there's no specific reason why I'm doing this. It's just that this is a big equation. Okay, so repeating it, it will because in the f of 1 comma 2 that we found, okay, fx and fi both have the same equation. So I'm just writing this as a t to simplify the equation. Okay, so now my tangent point equation was value of function at the point plus fx x minus you can say, let me write that, x naught plus fy y minus y naught, where x naught and y naught is the point on which we are finding the derivative. Okay, and let's write this also as x naught or y naught. So function value was this under root d minus a minus 4b divided by under root of c plus, I am considering this as t, so this is basically here negative a by t, and this is here negative 2b by t. Okay, so I can multiply this by under root d minus a minus 4b in the numerator and also in the denominator, right? This will not gonna change by
Yes,
my
sir.
equation. Okay, so in the above part it would be this, while in the denominator part it would be my t that I have considered. Okay, so this minus 2b by t. Okay, so now just take the, this t would go here, so it would be t times there, and it would be minus a, oh sorry, I forgot this part. Okay, uh, x minus 1 y minus 2. So here after it would be a times x minus 1 minus 2b times y minus 2. Okay, this part I have forgotten before. So you got t dot z equal to d minus a minus 4b from here minus ax plus a minus 2by plus 4b. So this will cancel out, this will cancel out. So I got d, just taking this negative term to the left hand side, it would be ax plus 2by plus t times z. Okay, and you can replace this t with this expression again. Okay, so you will get ax plus 2by plus under root of c times d minus a minus 4b times z. Okay, and this is equal to d, and this is the second option. Okay, ax plus 2by plus under root of c times dA minus 4b times z equal to d. Any doubt in this question or in the tangent plane part?
Sir, can you please explain it again how to find out this?
Okay, okay. So we need to find the tangent plane of the function f of x comma y, okay, at the point 1 comma 2. Okay, so my point x naught comma y naught here is 1 comma 2. This is my function. So let's first find the function value at the point 1 comma 2. So my function value at the point 1 comma 2 is just simply plug in x equal to 1 and y equal to 2 in the expression here. So I'll get 1 by root c under root of d minus a minus 4b. If you put x equal to 1, x square 1, so minus a, y equal to 2, 2 square 4, so negative 4b. So So this is my function value. Next step was find the partial derivative with respect to each variable. So I first found the partial derivative with respect to x. Okay, as we have already seen how to find the partial derivative for this type of function in the previous question. So I just simply wrote it, okay, directly, that the partial derivative would be negative ax divided by under root of c times under root of d minus ax square minus by square. Same would be the for the partial derivative with respect to y. Okay, it's just that in place of x, it will come as y. Okay, but we need to find the partial derivative at the given point. My point that was given to me was 1 comma 2. So just put 1 comma 2 in the partial derivative of x that I got. So just put x equal to 1 and y equal to 2 here also. So it will be negative a divided by under root of d minus a minus 4b multiplied with under root of c. Same for the with respect to y also. Okay. On putting y equal to 2, I got numerator negative 2b, in the denominator same as the partial derivative with respect to x case. Okay, because these are basically the same repeating terms and these are the long expression, I just simply assume that this under root of c times under root of d minus a minus 4b is equal to t, to just simplify the equation so that it looks good, okay, and easy to solve. Okay, now how to find the tangent plane? The equation to find the tangent line or equation was z is equal to function value at the given point x naught comma y naught plus partial derivative with respect to each variable multiplied with x minus x naught. Okay, like first partial derivative with respect to x and x minus x naught, partial derivative with respect to y, y minus y naught. If there was more variable, then partial derivative with respect to that variable multiply. Let's say if there are like r variable also, then partial derivative with respect to r multiplied with r minus r naught. Okay, there were one more point, but because it's just two variable function.
So
Yes,
here x naught, y naught is the point where that is to be determined. X
yeah,
naught,
the
y
where,
naught.
yeah, it is a point on which you are finding the tangent, that is 1 comma 2.
Okay,
Okay,
fine, fine. Yeah.
understand. Yeah, okay. So the function value that I got was this only. Okay, under root of d minus a minus 4b divided by under root of c. My partial derivative that I got was the negative a by t. Okay, I have considered this expression as the t. Okay, and partial derivative with respect to y at the point 1 comma 2 I got was the negative 2b by t. Okay, and I'm multiplying with x minus x naught, that is x minus 1, y minus y naught, that is y minus 2. Okay, now in the function value that I got, okay, I am multiplying this numerator and denominator with the same, that is I'm multiplying numerator with under root of d minus a minus 4b and also dividing it by under root of d minus a minus 4b. This is not going to change my equation because this will cancel out and it will be again the same equation. Okay, but the reason to do this is because I will get the numerator same. Oh, sorry, numerator not denominator. I will get the numerator denominator same. Okay, so when you do the product of these two, the root will cancel out and you will just get the expression of the inside of the root, that is d minus a minus 4b. In here it is negative a times x minus 1 and here it is negative 2b times y minus 2. When you take the uh, subtraction, okay, this t will go here, it would be t dot z. This is equal to d minus a minus 4b from here. Then this negative a times x minus 1 and this here negative 2b times y minus 2. Okay, so t dot z here we got d minus a minus 4b, just simplifying it, negative ax plus a, this negative and negative will become plus. Same for here, negative 2b plus 4b. Okay, so this positive and negative will cancel out, positive negative 4b will cancel out. I will just left with d minus ax minus 2by. Okay, so if I just send these negative terms to the RHS side, I will just get let uh, d is equal to ax plus 2by plus tz. Okay, and I'm just putting here the value of t, that is under root of c times t minus a minus 4b. Okay, which is the second expression. Got it?
Yes, sir. Yes.
Okay. Yeah. So in the single variable case for the calculus, we studied the tangent line. Okay, and also
Excuse me, sir.
yes.
Sorry to disturb, sir. Can you please move to
Yeah.
the previous question?
Okay. Okay.
Sir, here we have to find the equation of the tangent plane, right?
Yeah.
Uh, so, uh, so like this d is equal to this. This is the equation, right, sir?
Yeah. Yeah. Correct.
Okay.
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 This is the equation that you got. Okay.
Okay, sir. Sir, can we here use instead of z like any other variable like w or like ma'am
Uh,
told in the lecture video? Like that, can we
uh,
use? Can we do that here?
yeah. Generally, we can use, but as in the question, it is z is equal to f of x comma y. So that's why if
Okay.
you are using. Okay.
Okay, sir.
Generally, we use z, but it's our choice. We can use any variable. Okay. And
So we can use any variable, right, sir?
yeah, basically,
Okay,
what is
sir.
the tangent plane? Okay, in the next slide, we have the tangent plane equation on line. Okay, is basically the linear approximation, right? In single variable case, also we studied this. The tangent line equation that we got is basically the linear approximation of the function at that point. That means, in simpler terms, you can say how my function would behave around that point if it was a linear function, or what would be the expression for that linear function is what we call as a linear approximation of the function at that point. Okay, so it's just that the expression to find the method would be the same for the tangent line. Okay, it's just that here we are using z is equal to f of a tilde plus that, like that, and we will just use this as a l of f at the point x naught comma y naught is equal to function value at x naught comma y naught plus fx times x minus x naught plus fy times y minus y naught. Okay, and you can simply just move the formula to three variable, four variable. Okay, you can just simply expand this the same formula. Okay, generally in the exams you will be asked for, yeah.
Sir, you said that a linear approximation means that you express a function as a linear expression. So, sir, that I could not understand like what that meant.
And not the express, you can what I was telling, that linear
Uh,
approximation for a function at a given point means my function need not to be always linear, right? It can be curved or something like that, right? Can be
yes, sir.
any
Yes, sir.
type. Okay, so for the
Yes, sir.
function, just okay, at that given point, let's say we are just like for the example of this function at the given point 0 comma 1. Okay, now for this point, if I consider that my function would behave as a linear, that means my linear function, that is as a line, equation of line that we say. Okay, or the your plane. Okay, that is called as a linear function. Okay, if that
Yes, sir.
my function is a behave, then what would be the equation for that line or plane, or
Okay, sir.
okay. So this is basically the same, the tangent plane or hyperplane equation. Okay, it's just that it is a different name for that. Okay. So linear approximation, same approach, same, everything will be the same. Okay, just like how we did for the tangent plane. So just take an example. F of x comma y is equal to y e power x minus 1 by 4 times x square plus y square. Okay, we need to find the linear approximation of the function at the point 0 comma 1. Okay, so we denote my linear approximation generally L subscript f x comma y. Okay, this is first we need to find the function value at the point 0 comma 1 plus partial derivative of the function with respect to x at the point 0, 1 multiplied x minus 0 plus partial derivative with respect to y at the point 0, 1 multiplied with y minus 1. Okay. So what will be the function value at the point 0, 1? Just put x equal to 0 and y equal to 1 in this equation. So if you put x equal to 0,
3 by
e
4.
power 0, yeah, e by 4. This will be 1, okay, 1 by 4. Yeah, 3 by 4 you will get. Because y e power x is 1 and here x square is 0, y square is 1. So 1 minus 1 by 4 you will get 3 by 4. Okay. So partial derivative with respect to x at the point 0, 1. What would be the partial derivative with respect to x or the given function?
I got, sir, y e to the power x minus x by 2.
Okay, correct. And if we put just x equal to 0 and y equal to 1, I will get 1. Right? Yeah. Because this x is equal to 0 by 2, so it would be 0. Okay, and this expression is 1. Now, what about the case for partial derivative with respect to y? What would be the partial
I don't
derivative?
calculate it, sir.
Ex
Ex
minus 1 by 4 into 2y. That is minus y by 2.
by 2. Same. Yeah, correct. So just put x equal to 0 and y equal to 1. So 1 minus half, that is half. Okay. So just plug in this value in the given expression. So linear function or linear approximation of the function at the point 1, 2 is my function value was 3 by 4 plus I got the derivative as with respect to x is 1. So 1 times x minus 0 plus derivative with respect to y was 1 by 2. So 1 by 2 minus y minus coordinate of y is 1. Or just simplify it, x plus half y minus half. So you get x plus y by 2. 3 by 4 minus 1 by 2 is 1 by 4. Okay, so this is my linear approximation for the function. And option C. Okay, any doubt in this question? No? Okay.
Simple.
Yeah. Okay. So in week 10, professor just introduced the concept of critical points. Okay. The formal way, like how to find the critical point, how to check whether it is a local maxima or minima, we learn that in week 11. Okay. So week 11 we use the higher of the partial derivative and Hessian matrix test to determine whether it is a local maximum or minimum. But in week 10 we just have the introduction, like what is the critical point and just a general approach to find the critical points. Okay, so any point for any scalar valued function f, okay, is called to be a critical point if it satisfies these two conditions. Okay, this is the or condition, remember. That means either it should satisfy the first condition or it should satisfy the second condition. Okay, or just remember this. First condition is gradient of f at that point is equal to 0. That means in simpler language we can say partial derivative with respect to each variable at the point a1, a2 till an is 0. Or my second condition is at least one of the fxi, that means at least one of the partial derivative with respect to some variable, okay, at least with respect to one variable at least, it doesn't exist. Okay, so either this condition should satisfy or this should satisfy. Okay, only in that case we consider that point as a critical point. Okay, So steps to find critical point is first try to find the partial derivative, okay, with respect to each variable. Either it can happen that one of the partial derivative does not exist, then we can just simply say the given point is the critical point, okay. Otherwise, try to find all such points a1, a2 till an. For that, partial derivative with respect to all variable at those points is equal to 0, and simultaneously that means this should happen for each variable case, okay. So that means the point which you are claiming that it is a critical point, either at that point one of the partial derivative does not exist, or at those point partial derivative with respect to each variable is 0, okay. Got it?
Excuse me, sir. So here this variable which whose partial derivative should not exist, that variable can be any variable, not specifically x.
uh, yeah, the xi here I have written that is it is xi, okay. That means it can be any variable, okay. It's not x, it is xi.
Okay.
Any ith variable it can be, okay.
Sir, if it is
Yeah.
does not exist, what does it mean by does not exist? It would be like imagine a complex number or something.
Yeah, I guess in this one example where it doesn't exist, it would be like, yeah, that as you said, it would be like either complex number or something you will get, okay.
Okay, sir.
Like under root of -2, like that, okay. So does not exist case that is there, okay. So f function f, here we are basically defining the condition for local minimum and maximum. It is the same that we studied in our single variable case, that at the point a1, a2 till an, this point is called to be local minimum if the function value at this point is minimum around its open ball. Open ball means around the in our single variable case, let's say this is the curve, okay, okay. Okay. So in my single variable case, this point can be considered as a local minimum, okay, because around this point all value was greater than this, okay. So and this you can expand this in the multivariable case also, that a point a1, a2 till an is called to be local minimum if around that point all values of function comes out to be greater than that, okay. And just reverse of that would be my local maximum, that at the point a1, a2 till an, this point is called to be local maximum when my function value at this point is greater than my function value around the point, around like whatever the point, just like for this case, okay, around this point whatever the point you will take, okay, would have the function value lower than this, okay, smaller than this. So this would be considered as a local maximum, while this can be considered as local minimum, okay. Local maximum,
Sir,
yeah.
please
Yes.
explain saddle point also here. Saddle point.
Yeah, saddle point. Yeah, the saddle point is simply not all local extrema are the critical point, and not all critical point are local extremum. And basically, those critical point at which the gradient exists and is 0, but not our local extrema, are called the saddle point. That means around a saddle, like how you can have you seen the saddle on the horse? Okay, it would be in that
Yes.
shape, neither it would be like maximum or minimum, okay. In our single variable case we use our derivative test, second derivative test, right? First we find the derivative of the function, equate it to 0, whatever the point come out, okay. uh, at that point we take the second derivative of the function and check what is
Sir,
the value.
can you Sir, can you please draw one figure and can you please try to show the saddle point? How the plot will be in that case?
Okay, figure.
Yeah, like you have drawn
See,
that maximum and the minimum local point. That how the shape of the this curve will be, sir.
it would be like this. Okay, in the single variable case we check. Okay, as here. Okay, the point would be minimum also around the point. Okay, if you go here, while around the point above it would be maximum also. Okay, so neither it is maximum, neither it is minimum. Okay,
Yes, sir. Yes, sir.
okay, around this point. If you go below, it would be minimum. If you go above, it will be maximum.
Maximum. Yeah.
Okay, so in my single variable, what we did was we did the derivative test. That is, first take the derivative of the function, equate it to zero. Okay, whatever the point comes out, we call it as a critical point. And to find the local maximum or minimum, we take the second derivative and check at that point what is the function value comes out. If it comes out greater than 0, we call it as a local minimum. If it comes out less than 0, we call it as a local maximum. If it comes out equal to 0, when we say test is inconclusive, right? So here also
Yes,
we
sir.
have Hessian matrix test that basically we study in week 11. Okay. So it,
Excuse me, sir. Can
yes.
you please explain the two local minima and the local maxima points? I missed it. Uh,
Uh,
the points two.
loc-
Yes, these two
yeah.
points.
Any
Please, sir.
point, okay, any point, if you are claiming that my point a1 a2 till an is a local minimum, that means my function value at that point would be smallest among the point around its neighbor. Okay, but around its neighbor, if you take any point, my function value
Okay.
comes out to be lower than this. For example, here, okay, this point, if you take any point around this, okay, the function value, it would this point would have the lowest function value, while any point around this neighbor would have higher function value, right? Okay,
Yes,
and
sir.
this the opposite case would be my local maximum. That if you take any uh, point around this neighbor, okay, any point around its neighbor, then that function value would be smaller than this. Okay, it would have the highest function value. Okay, that would be called as local maximum. However, if you see, if I only bound my function till this point, then these points are also called, can be called as the global maximum and global minimum,
Yes, sir.
right? Okay, we cannot always find the global minimum and maximum. For some function we can find because it is easy to see, like for the function, if I say x square plus y square, okay, this function is always positive, we know. Okay, it would be remain always in the positive axis. Okay, so the minimum value we can find is 0. That is when x and y both are 0, so
Yes,
it
sir.
could also be a global minimum. Okay, but we cannot find the global maximum for the same function, right? So
Yes, sir. We cannot.
okay, so global maximum and minimum. Okay, a global or absolute maximum minimum is a point for which the function value is maximum or minimum amongst all the points in the domain. Okay, just like I take the example of for x square plus y square. Okay, so its global minimum would be 0. Okay, and if I just take this as a minus x square minus y square, then its global maximum we can find, that is 0 again. Okay, it's just the, you can say, mirror image of my above function, right? Mirror image of this function. Okay. But yeah, it always exists when my domain is closed and bounded. That means if I can bound my function, then it always exists. But if I don't bound it, then we cannot find. Okay, just like for this case. Okay, let's consider two variable case, that is f of x equal to x square. Okay, it would be like this quadratic, okay, parabola. Okay, now its global minimum is here. Okay, global maximum we can find cannot find because it's going till infinite. But if I can bound this function till here, let's say, okay, that I only need to find global maximum for the function for this rectangular bound only. Okay, then we can find that the global maximum is occurring at this point. Okay, so it always exists when I bound my function, but if I don't do it, then we cannot say that it always exists. Okay, got it?
Yes, sir.
Yeah. So in week 10, basically you will just ask to find the critical points. Okay, uh, because whether it is a local maximum or minimum, we need to do the Hessian test that we will study in week 11. So now, yes, I have taken only the question on which we need to find just the critical point.
But I guess global minimum was also there in week 10.
Yeah, that is just one question in which we are basically bounding my function. Okay, in which we bound my function under some rectangle or square, in which the process is same. Okay, what's the process is that first find the critical point and also find the what is my function value on the border region. Okay, just like if I'm bounding my function on the rectangular, okay, I have one function. Okay, I have one function, okay, like that, and I am bounding it by some rectangular region. Okay, first find the critical point. Okay, then second thing you need to do is find the function value at the border region, that is what is my maximum or minimum value coming out along this boundary, along this boundary, along these corners. Okay, okay, along these corners that you need to find and compare these value. Okay, that's all is there. So okay, and you just need to compare them and you can get your global maximum or minimum for that bounded region. So for this question, however, it is just asking you to which of the following are true about f. So here we need to first find the derivative with respect to x and y, partial derivative with respect to x and y for the given function f. So with respect to x, it would be x cubed by 3, so it would be just x square plus 2y minus 6. Okay. With y, it would be 2y plus 2x minus 3. Okay. So first option is telling that fy equal to 0 is a straight line passing through the origin. Is it true? First
No.
option. No, right? Because if you see this equation only, 2y plus 2x minus 3, this is basically you can say the equation for any affine plane. Okay, affine space, affine line equation, right? Okay, if this 3 will not be there, then we can say it would be a straight line passing through the horizon. Okay, but it's an affine plane equation. Okay, it's translated by one vector. Okay, so that's why this is not correct. For now, for the remaining options, we need to basically equate my partial derivative to 0. Okay, so if I equate a fx
Sir,
equal to, yes.
sir, please explain this affine plane that you were talking about in this question. This why is it
Okay,
not passing through origin, sir? Please.
yeah, okay, if I'm giving you one vector, let's say x comma y, such that x is equal to y plus 1. Okay, and another vector, another space, x is equal to y. Okay, we have stated that this is my vector space, while this is not. Okay, this one here is affine space.
Affine, yes, sir.
Okay, translation by the vector 0 comma 1. Okay, we are translating. Okay, same here also is happening. We have 2y plus 2x minus 3. So basically I can write that this is a affine plane x comma y such that x is equal to 3 minus 2y by 2. Okay, or more simplify, you can do minus 2y minus y plus 3 by 2. Okay, so that constant part is coming here, right? Just like here.
Yes, sir.
Okay, if it was equal to 0, okay, any general affine plane, how it will look? X comma y such that ax plus by equal to 0. Okay, if this k is equal to 0, then it is in vector space. If this k is any other scalar number
Then it is
other than
fine, sir.
affine, even at the case for 0, it is also an affine space because every vector space is an affine space also. Okay, but it will not pass through the origin if it is not equal to 0. Okay, so that's why fy is equal to 0 is not a straight line passing through the origin. So yeah, now we need to find the critical point. We need to equate my partial derivative equal to 0. Okay, so I got was x square plus 2y minus 6 and 2y plus 2x minus 3. Okay, now from here, if I choose 2y equal to 3 minus 2x and put this value of 2y in this equation, I got x square plus 3 minus 2x minus 6 equal to 0. X square minus 2x minus 3 is equal to 0. And I can write this also. Okay, this is the simple factorial, right? So x equal to 3 or negative 1. Okay, now just put these value of x in this equation. So 2y equal to 3. If I put x equal to 3, then I will get 3 minus 6 negative 3 2y. So y is equal to negative 3 by 2. On x equal to negative 1, I will get 2y equal to 3 minus 2 minus 1. 3 plus 2, 5 by 2. Okay. So the critical points that I got is, if x is 3, my value of y was negative 3 by 2. If x is 1, negative 1, my value was 5 by 2. Okay. So these two are the critical points. Are they matching with the options? Yeah. Yeah. Okay. So these are the critical points. And the third option is basically saying the partial derivative at the critical point would be equal to 0, obviously. Okay. While in the fourth option, we are finding the partial derivative with the critical point. It should be equal to 0, not 2. Okay. So it would be incorrect. Got it? Okay. Then, yes. Any doubt?
Sir, sir here, uh, sir, how this x is equals to x, 3 minus 1, y is minus 3 by 2, 5 by.
Yeah.
Sir,
See,
how do you arrange them in pairs, sir, in this?
when I'm putting x equal to 3 in this equation, I am getting y
Yes, sir.
equal to negative 3 by 2. Okay.
Oh,
So
okay.
on the value of 3, I will getting this. Okay. So that's how I
Okay.
arranged.
Yes, sir. Okay, sir. Thank you.
Yeah. So one more question is here. Okay. Which of the following options are correct? Okay. So first option, the minimum value of the function f of x comma y equal to x square plus y square plus 8 is 0. Is it correct?
No, sir.
No. Then what would be the minimum value?
8.
8, right? Because it is an always positive function. Okay. So its minimum will occur when x and y both are 0. Okay. So, and when x and y are 0, the function value is 8, not 0. And that would be its minimum value. Okay. option 2, the minimum value of the function is 0. Is this is correct?
No, it's not correct.
It's not.
Fx is 2x minus 4. If you equate that, we will get x equal to 2.
Fx is 2x minus 4, not 8. And then you will get x.
It's correct.
X equal to 2.
Yeah. Okay. See,
Oh,
what it
okay.
is asking,
Yes, yes, got it.
that
Got it.
you will get the critical point, not the function value. Okay.
Yes, yes.
It's
Got
asking you to find the minimum value. Okay. But see, one thing, how can you identify that the point that you are getting is local minimum or minimum value? Not the, it can be maximum also, because you will only get the critical point. Okay.
Sir, we can make squares here.
Yeah, correct. That's what you need to do.
X minus
X
2 and
square
y
plus
minus
y
2.
square plus 8 minus 4x minus 4y. Okay. If I just manipulate the function like this, plus y square minus 4y plus 4. Okay. I split this 8 into these 4. Okay. Then what it is? It is x minus 2 square, and this is y minus 2 square. Okay. So
Sir.
this you can consider, yes.
No, no, I was saying nothing, sir. I was just saying yes, sir.
Yeah, this you can consider as a capital X and again y. Okay, so this is again the same positive function. It will always be positive. Okay, and the minimum value for this type of function is 0. Okay, the way we were getting, if you want to go through with the critical point, then you need to also prove that the point that you are getting is a local minimum, not maximum. Okay, but till week 10 we don't know how to check for the point whether it is a local minimum or maximum. Okay, so with that you cannot sure about. Okay, now for option C, the maximum value of the function this is 0. Is it correct?
Yes, sir.
Yeah, this is correct. Okay, because it is just simply negative of x square plus y square. This function has minimum value 0, and as you are multiplying it with the negative, then the most minimum value would become the most maximum value. Okay, so the maximum value would become the 0 here.
Sir, I didn't understand your concept with these questions.
See, here it is negative x square minus negative y square. I can simply write it as a negative of x square plus y square. Okay, now
Okay.
when this function inside x square plus y square will attain its minimum value, only then this whole function will attain its maximum value, right? Because it is the negative of that. Okay. In negative, if you see the number line, right? The smallest the number in the negative, the higher it is, right?
Okay.
Correct? Okay. So when this x square plus y square would be minimum, okay, and when you multiply this with the negative sign, it would become the maximum for that, right?
Yes, sir.
Okay, so that's why this inside would be minimum at 0 comma 0. Okay, so at that point you will get the minimum value as 0 and negative times 0 is 0, so that would become the maximum value for this function. Okay,
Okay, sir.
now for the fourth option, maximum value for the function x square plus y square minus 2x plus 1 is 0. Is it correct?
No, sir.
No, correct. This 0 is actually the minimum value. Now, how can we check? Same approach that we did for the option 2, that is x square plus y square minus 2x plus 1. So I can write it as x minus 1 whole square plus y square. Okay, these three terms together will become the x minus 1 whole square and plus y square. So again, it's the same thing here. Okay, so the minimum value would be 0, not the maximum value. In the question, it is telling that it is the maximum value. So that's it, true. Any doubt in this question?
No, sir.
Yeah. So furthermore, we have some more practice question. But before that, if you guys have any doubt in week 9 or 10, that you can ask. Or if not, then we can proceed with the questions. Anybody has any doubt in week 10 concept?
No, sir.
No? Okay. Then let's solve more questions. Okay.
Sir, I have a
Yeah.
question.
Yeah. Please.
General answer, but in website, our portal, week 11
Okay.
and 12 has same videos and same
Uh,
like something.
Okay, okay. So actually, the thing is, Maths 1 and Maths 2 both don't have week 12 content. Okay, both Maths 1 and Maths 2 are just of 11 weeks. Before they were 12 weeks. Okay, but later in January 2022, the Maths 1 and Maths 2 both syllabus has changed. Okay, and after the term January 2022, uh, they become the 11-week content. Okay, now I don't know why they have doing this now. From May 2023, they are just uh, putting one extra week 12, that is just the dummy week of week 11, okay, as in separate for the week 12. So I guess just the fill the blank space for week 12, okay.
Okay,
So
sir.
don't need to bother about that. Okay, it's the same week 12, it's just the dummy week. Okay.
Okay, sir.
Yeah. Okay. So question number 6. At the point P naught, the function f of x comma y has a derivative 2 root 2 in the direction of this vector and a derivative of 5 in this direction. Find the derivative of function x comma y at the point P naught, that is the same 1 comma 2, in the direction of negative 1 comma 2. Enter the answer correct to two decimal place. Assume gradient of the function exists in continuum. It is in its domain. Okay. So how we can solve this question? Does anybody has any approach? What we have given, that we have one function
Uh,
f. Okay, we have given one point 1 comma 2. Okay, and last line is telling that gradient of function exists and continuous in its domain. Okay, so the derivative that we have given, we can find this derivative using gradient of f, right? That is gradient of f times my unit vector. Okay. So with respect to this 1 by root 2 and 1 by root 2, my derivative is 2 by root 2. With respect to 0 comma 1, my derivative is 5. Then I need to find my derivative in the direction negative 1 comma 2. Okay, so how we can find?
Should we make equations of f of
Yeah,
x and f of y?
yeah. Okay, so what equation you will make?
Means
Okay,
f of x into 1 by root 2 and f of y into 1 by root 2, like that.
why they need to be 1 by root 2 f of x?
The
See,
first
just
equation.
first read the question carefully. Okay, we have defining 1.1 comma 2. Okay, and to the whole question, whatever I am doing is doing at this point only. Okay, at this specific point. Okay, so if I take the derivative of one function, okay, I am taking the derivative of this function fx and fy. I am taking the partial derivative. Gradient of f is just the vector with fx and fy. Okay, gradient of f is fx comma fy. Okay, and I am finding this gradient of f at the point 1 comma 2, because all the derivative are taken place along this point only. Okay, it's just that we are just changing the direction every time. Okay, so does this gradient of function going to change at this point, or it will remain constant throughout the point?
Constant.
Yeah, correct. It would be constant, right? Because we are basically putting my x equal to 1 and y equal to 2 in that gradient function. Okay. So you will get some numbers, right? Some point as a vector for the gradient. Okay. So that would remain constant for the term. Okay. Throughout whole time. Okay. And we basically need to find the gradient of function f at the point 1 comma 2 unit dot product with this vector. Okay. So first we need to find what is my value of gradient of f at the point 1 comma 2. For that I have given two more information, that is gradient of f at this gradient of f multiplied with this unit vector, the derivative is this gradient of f at the point 1 comma 2 multiplied with this unit vector, okay, is fine. So let me consider my fx to be a, fy to be b. This is at the point 1 comma 2. Okay, that's why I have considered them as a scalar. Okay, if it was not given that they are not at some specific point, then I cannot consider them as some scalar quantity. Okay, but because they are we are just fixing one point, so at one specific point if we fix, then they would be constant. Okay, so gradient of f at the point 1 comma 2 is a comma b. So now we just need to plug in this value here, that is a comma v dot product with 1 by root 2 comma 1 by root 2 is 2 root 2. So that is wait, yeah, a plus b by root 2 equal to 2 root 2. So we'll get a plus b equal to 4. This is my first equation. From second equation, gradient of f dot product with this 0 comma 1, this is 5. So I got b equal to 5. Plug in the value of b here, you got a equal to negative 1. Okay, so gradient of f at the point 1 comma 2 is negative 1 comma 5. Now we need to find the derivative of the function in this direction. Okay. Remember always, whenever we need to find the gradient, we are finding my derivative using gradient of f dot unit vector. That vector has to be unit vector, that is the norm of that vector has to be 1. But the norm of this vector here is not 1, right? So we need to normalize this vector, that is dividing by its norm. So that we can do is 415. So negative 1 by root 5 comma 2 by root 5. Correct? So it is just simply negative 1 by 5 dot product with negative 1 by root 5 comma 2 by root 5. So you'll get 1 by root 5 plus 10 by root 5, that is 11 by root 5. Okay, now if you just divide 11 by root 5, it would be around 4.91. Okay, any doubt in this question?
So would you please run down the process quickly?
Okay, yeah, sure. Okay, so we have in the question we have given one specific point 1 comma 2. Okay, and at that point we are taking derivative with respect to three different unit vector. Okay, one is this, second is this, and the third one is this. If I taking derivative along this direction, I am getting this derivative 2 root 2. If I am taking derivative along this direction, I am getting this as a derivative. So I need to find my derivative along this direction. Okay, so we know that the gradient of a function at a particular point would be fixed, or you can say constant always. Okay, So that because we are finding it at one particular point 1 comma 2, so it will be fixed at that point. Okay, so as in the question it is given that gradient of function exists and continuous, so I can use my gradient method to find the directional derivative, that is gradient of f at the point dot product with unit vector. Okay, so gradient of f at the point 1 comma 2, I'm considering that as a comma b. Okay, and then just plugging these value here, whatever the given in the question, that derivative in the direction of 1 by root 2 and 1 by root 2 is 2 root 2. So gradient of function f at the point 1 comma 2 is a comma b. Dot product with 1 by root 2 comma 1 by root 2 is equal to 2 root 2. We just simplify, you will get a plus b equal to 4. Next it is telling the derivative is 5 in the direction 0 comma 1. So gradient of f at the point 1 comma 2 in the direction 0 comma 1, it is 5. So if you take the dot product, it will be just simply b equal to 5. Okay, just plug in this value here, you will get a equal to negative 1. So I got my gradient of function f at the point 1 comma 2 as negative 1 comma 5. Now later it is asking you to find the derivative of the function in this direction. Now every time whenever it is asking you to find the derivative in some specific direction, we always need to confirm that the given vector has to be unit vector. Okay, as this vector is not our unit vector, as the norm of this vector is not 1, we need to normalize this, that is simply dividing this vector by its norm. The norm of this vector would be just 1 square plus 2 square, that is 5 under root of 5. So I'm just dividing this vector by under root of 5, so it will be negative 1 by root 5 comma 2 by root 5. And rest is again same, gradient of function f at the point 1 comma 2 dot product with unit vector, I will get my derivative is 11 by root 5. Okay, so if you just
Yes, thanks.
calculate the value, it would be 4.91. Okay, next question. We have a function from R2 to R in the question, that is x square plus y square. Okay, consider the following algorithm: x of n plus 1 is equal to xn minus h times gradient of f at xn. Okay. Now we have seen these type of function in starting week, right? In week 2 and week 3, these are the recurrence relation, right? Where we have p of something like, we have matrix p of xn plus 1 equal to some xn, right? In week 2 and week 3 we have solved this type of question where we dealt with recurrence relations, right? Okay, so the same type of function is given here. Okay, that these xn plus 1 and xn are the vectors. Okay, this h we are fixing to be some value 0.25, and my initial vector here is 1 comma 3. Okay. So if I just simplify this, given here is xn plus 1 is equal to xn minus 0.25 gradient of f at the point xn. Okay, then it is asking that which of the following points does the algorithm converges to. Okay, so basically we need to see, we have given the x naught to be 1 comma 3. Okay, so can from x naught we can find x1? Can we do that?
Yes,
Yes,
sir.
sir. Yes.
Yeah, right. Just put what would be x1 here is 1 comma 3 minus 0.25 gradient of the function at 1 comma 3. What is gradient? What is my function? X square plus y square. What is the gradient of f at the point x comma y?
2x.
Comma 2y.
2x money.
2x comma 2y. Okay, we need to find this gradient. Similarly you can find x2 when you find x1 and x3. Okay. So what it is asking, which among the following points does the algorithm converges to? That means this is like the limit question that we solved in our maths 1 course. That is, we have given one sequence. Okay, the sequence is going on x1, x2, x3 till xn. So does this algorithm converge to some specific point or does not? Okay, so that's what I need to show here. So for that, first calculate x1. Okay, so x1 here is 1 by 3 minus 0.25 times gradient of f at the point 1 comma 3. Gradient of f we got is 2x comma 2y. So x1 is 1 comma 3 minus 0.25. If you put x equal to 1 and y equal to 3 in this equation, you will get 2 comma 6, right? Okay, so you'll get 1 comma
So
3. Yes.
X1.
Uh, Sorry, what?
Sir, you write the equation x n plus 1 is equal to
Okay,
x
okay.
n minus is
Yeah, this is actually algorithm that is given to us already. Okay, if you remember from week 2 and week 3, we have solved one recurrence relation question, right? P of xn plus 1 equal to xn, right? There also we encountered these type of functions, right? Okay, same type of you can say kind of function is given to us. X of n xn plus 1 is equal to xn minus h times gradient of f at xn. We are fixing my h to be 0.25. My initial vector is 1 comma 3. Okay, so x naught is 1 comma 3. So from x naught I can find x1. Okay, gradient of f we have already found. We have just simple x square plus y square. Okay,
uh, after writing the equation, you write x naught is equal to 1 comma 0, and then
x1 equal
x1
to,
is equal to
I
x
have written
x
x
naught is equal to
1 comma 3. Yeah,
here on 1 comma 3. Then
yes.
how you write x comma 1 is equal to
Remember this. This is what? Here xn. So this is my xn right here. So it will be what? N plus 1. That is x1, right?
yes sir.
Okay, and here also it is xn, that is x naught here. Put n
Okay
equal
sir,
to
I
0
got it.
in this equation. Basically, if you put n equal to 0 in this function, okay, at the case of n equal to 0, you will get this, right? X1 equal to
Okay sir.
x naught minus 0.25. So what would be the value of x1 here? 0.25 to zero point 0.5. This is 1.5. So you will get 0.5 comma 1.5. We got x1. Similarly, now put n equal to 2 in the given function. Sorry, n equal to 1 in the given function. So x2 would be what? X1 minus 0.25 gradient of f at the point x1. X1 was this, 0.5 comma 1.5 minus 0.25 gradient of function at the point x1. Gradient of function was 2x comma 2y. So that is zero point 0.5. Okay, so now you got this zero point 0.5 comma 1.5 minus 0.25 comma 0.75. So if you just subtract it, you'll get 0.25 comma 1.5 minus 0.75. So 150 is 75.
0.75.
Point. Okay. Yes. Any doubt? Yeah.
Sir, we need to check like this.
Yeah. See, what we need to do here in the question, it is asking you to which of the following point does the algorithm converges to. Okay, so it simply means you need to calculate some point x1, x2, x3, x4 like that. Okay, and you need to find whether this algorithm converges to some specific point or not. That means the limit exists or not. Simply like that. Okay. So we find x1, we find x2. Let's find one more point. Okay, x3. So x3 is just simply x2 minus 0.25 gradient of f x2. Okay, I will just quickly do it. Okay, because now we know how to calculate these. 0.25 double of it. Point 125. 25. 0.37. You will get the okay. So this is my x3. Now comes the observation part. Okay, we started with x naught 1 comma 3. We got our x1 was 5 comma 1.5. We got our x2 was 0.25 comma 0.75. We got my x3 was 0.125 comma 0.375, and this is happening. Now are you able to see
Sir,
any yes,
half of reading one.
yeah, correct. Okay, if you see the pattern here, these basically are getting half. Okay, each coordinate of a vector is getting half from the previous one. Okay, to find x1, it is just the half of the vector x0. x2 is nothing but half of vector x1, and same like that. Okay, so basically any n plus 1 vector is basically the half of the previous vector, right? So this dangerous looking recurrence relation is basically just the simpler relation. That is, x of n plus 1 is half of xn. Now, if I have a sequence where my first term is n, second is n by 2, third is n by 4, fourth is n by 8, like this, and I told you that limit of n tends to infinity, find the nth term. What would be the limit for that? If this is my sequence, if n tends to infinity, okay, oh, let's consider this n to be, let's say, 1. Okay, okay, this is my sequence now. 1, 1 by 2, 1 by 4, 1 by 8. Then what would be my nth term when n tends to infinity?
0.
0.
0. Yeah, correct. Okay, so this is also getting half. Okay, so for any nth vector, okay, when n tends to infinity, the algorithm converges to is the point 0 comma 0. Okay, so third option would be the correct. Got it? Any doubt in this question?
No, sir.
I will just still repeat this once again. We have given one function from R2 to R, defining my function to be x squared plus y square. Now consider one the following algorithm, that is x of n plus 1 is xn minus h times gradient of f at the point xn. Okay, so we are fixing my h to be 0.25 and my initial vector is 1 comma 3. Okay, so these are basically the recurrence relation. That means from the previous result that we got, we can find the new result. Okay, so if we have initial vector x naught, on putting the value of x naught in the equation here, n equal to 0, I can get the value of 0 plus 1, that is x1. So xn 1 comma 3, h we fix is 0.25, so minus 0.25 times gradient of the function at 1 comma 3. Gradient we calculated is 2x comma 2y. Okay, so at 1 comma 3 it would be 2 comma 6. Just simplify it, we got my x1. Similarly, when you put n equal to 1, you will get my x2 and x3. then we just observe that for each new vector, it is getting half from the previous vector. Okay, that is x of n plus 1 is nothing but the half of the x of n, the just previous vector. Okay, so if we have any series like that, that is we started with 1, then half, 1 by 4, 1 by 8. Okay, and this is going till n. When n tends to infinity, that is the n last term. Okay, if this series continues like that, this will convert this to 0. Okay, so if this algorithm goes like this, okay, the xn vector you will get would be 0 comma 0. Okay, so the following the algorithm converges to the point 0 comma 0. Okay,
So is it any end time question?
no, this is not the end term question. Okay,
Because the calculation is
yeah, no, this is not the end term question I said, but if you see, once you identify, okay, the calculation are not that much hard.
yes.
Okay. Yeah, it's just that I have taken more time. Okay, but like once you start doing this, like from here what is happening, whatever the vector I am getting here, I am getting that vector same. Okay, here also I am getting that vector same. Okay, so I will easily get the pattern. Okay, so usually these type of question, they always follow some kind of pattern or something, right? So you just need to identify that. Just like we check in the week 2 and 3, the recurrence relation like this, pxn plus 1 equal to x.
So these are from activity or practice
No, no, no.
assignments.
Uh, this is not from the course. Okay, some extra question that I took.
Sir, can you share that this PDF?
I will share this PDF in the folder. Okay, if you like, go on the
Master
discourse,
folder.
not the master folder. Uh, okay, like just a second. Okay, so I hope all of you have access to discourse. Okay, so if you go in the course category for the maths 2, okay, there you will find one post. It will be like, mostly it will be pinned. Okay, if it is not, you can always search the post using the search icon. That is, post name is maths 2 resources by ta. Okay, and this just go to the above post. Okay, first one. Okay, there you will find some resources. In that, the first would be the ta session folder. Okay, this link I will give you here also. Okay, but you can always access by logging to your discourse. Okay,
Okay, sir. Thank you.
this pdf will be uploaded here. This
This
question,
is the first option, correct?
yeah, the first option is correct, I guess. Yeah, but we have solved this question. I guess we have solved this. Okay, so it's just this. Okay, yeah. Okay, so it's just the same question again. Okay, f of x
What
com.
is the mean of 0 comma?
Sorry, or neighborhood of 0 comma 1. Basically the same thing.
What?
Uh, the open ball around that. Okay, it's the same thing. Basically, you need to find the linear approximation of the function at that point only. Okay, neighborhood means the same thing around open ball. Okay, around that point. So it would be the same. At that point only, you need to find the linear approximation. Okay, so we have already calculated this. Just f of 0 comma 1 is just 1. Fx would be, okay, ex y by exy dot y. So y square exy. So fx at 0 comma 1 would be 1 e, sorry, 1, right? Now fy y e power, right?
It is your xy.
Plus, because see, here it would be in the u dot v case, right? So first take the derivative, like y derivative of y, and ex would be the same, exi. Then derivative of this part, exy. So that would be exy, okay, dot x dot y. Okay, so basically exy you can take common, so we left with 1 plus xy. Okay, now fy at the point 0 comma 1 would be out for 1 plus 0 1. Okay, so linear approximation is function value at 0 comma 1 plus fx times x minus 0 plus fy times y minus 1. Function value if we quote is 1. Oh, okay. Function will, yeah, okay, it will cancel. 1 times x minus 0 plus 1 times y minus 1. Okay, so if you just simplify plus y minus 1, you will get x plus y. Okay, I hope there should not be any doubt for this question, right? First option is
No,
correct,
sir.
right? I didn't check before, it's just the same question. Okay, yeah. Ninth question, it is asking us to find the direction of steepest descent for the function cos x sin y tan z at the point x comma y comma z equal to pi by 4, pi by 6, pi by 4. Okay, so when is the direction of steepest descent occur? Is it in the direction of gradient or in the opposite direction of gradient? Anybody?
Opposite.
So same
Opposite
direction.
direction.
Negative step at this and negative direction, sir.
Yeah, negative. The steepest descent occur in the negative direction of the gradient. Okay, so we need to basically find the gradient only. No need to calculation. So first find the partial derivative with respect to x. So these basically sin y and tan z term are constant. Okay, only need to check with the cos x. So derivative of cos x is, what is the
Minus
derivative of,
Minus sin x.
yeah, minus sin x sin y and tan z. Okay, now fx at the point pi by 4 comma pi by 6, pi by 4 is negative sine pi by 4 times sine pi by 6 tan of pi by 4. So sine pi by 4 is 1 by root 2 negative. Sine pi by 6 is 1 by 2. What is the value of tan pi by 4? Anybody?
1.
Yeah, tan pi by 4 is tan 45. Okay, so sine pi by 4 is sine 45, 1 by root 2. Sine pi by 6 is sine 30. Okay, so sine 30 value is 1 by 2. So here it is negative 1 of 2 by 2. Now fy same. So yes, anybody saying something? So again for the y case also, the first and the second cos x and tan z would be the constant. Only change will happen in sin y. So derivative of sin y is, what would be the derivative of sin y?
Cos phi.
Yeah. So cos x, cos y, tan z. So fi at pi by 4, pi by 6, pi by 4 is cos pi by 4, cos pi by 6, tan pi by 4. Cos pi by 4, sin pi by 4 is same, 1 by root 2 multiplied. It will be root 3 by 2. Okay, the same, so root 3 by 2 root 2. Okay, now come for the case of partial derivative with respect to z. Okay, so again for the z case, cos x and sin y would be constant. Only take the derivative of tan z. So what would be the derivative of tan?
Sec square.
X, yeah, correct. So it will be cos x sin y secant square z. So fz at this point, cos pi by 4, sin pi by 6, secant square pi by 4. Okay. Cos pi by 4, 1 by root 2. Sin pi by 6, 1 by 2. Secant square pi by 4 is 2. Okay. So you got 1 by root 2. So basically what we got as my gradient at the point pi by 4, pi by 6 and pi by 4 is negative 1 by root 2, root 3 by 2 root 2 and 1 by root 2. Okay, so steepest ascent occur in the direction of gradient, steepest descent occur in the opposite direction of the gradient. Okay, so that is multiply this by negative vector. So 1 by 2 root 2, negative root 3 by 2 root 2, negative 1 by root 2. Okay, so first option,
Need to,
yes,
sir,
anything?
don't we need to go for the unit vector? The
That
norm of
is,
that and
that is if you need to find the value. Okay, if you need to find the
yeah,
value,
okay.
then we do. Okay. Like what would be, you can say the minimum value. Okay, when we find the minimum and maximum value, in which direction we say it will occur and what it will be. So minimum value occur in the negative direction of the gradient. Okay, so you can take the gradient vector as your unit vector. Okay, and in that direction only the minimum value occur. Okay, and you can calculate it. Okay, just dividing by its norm, so whatever it comes out would be your value. Okay. So here it is just asking you to find the direction of the steepest descent. Okay. So direction would be just the negative of the gradient vector. Okay. Any doubt in this question?
No, sir.
No. Now, final question for today. That is, we have a function 3x cube plus 4y square plus 10. We need to find the linear approximation for the function around the point 1 comma 1 and use it to compute the value of 1.1 comma 0.9 of the linear approximation. And then basically we need to find the difference of function value 1.1 and 0.9 from the linear approximation. Okay. So to find the linear approximation, we need to first find the function value. Okay, we are finding the linear approximation around the point 1 comma 1. So f of 1 comma 1 is 3 plus 4 17. Okay, now fx would be 9x square. Fx at the point 1 comma 1 is 9. Fy would be 8y. Fy at the point 1 comma 1 is simply 8. Okay, so linear approximation would be 17 plus x, sorry, 9 times x minus 1 plus 8 times y minus 1. So that is 17 plus 9x minus 9 plus 8y minus 8. So linear approximation you got is 9x plus 8y, as this will cancel. Okay, so we got the linear approximation. Now we need to compute this value, that is the linear approximation of the 1.1 and 0.9. So 1.1 and 0.9 is 9 times 1.1 plus 8 times 0.9. So 9.9 plus 9 at 72, 7.2. Okay, we got 17.1. So we need the difference of the function value and the linear approximation value. So function value at the point 1 comma 1 and 0.9. My function is described like this. Okay, so 3x cube plus 4y square plus 10, 1.1 cube plus 4 times 0.9 square is 10. So 11 cube is 1331. So 31, 9 square 81. Okay, and this is just a 10. Okay, now so you will get 3 3 is a 9, 3.993, 4 is a 32. Okay, 3 6. Okay, okay, so we got as 17.233. Okay. So difference is simply just this. (17.233) minus 17.1. You can consider this as a approximate 0.13. Okay, this is asking till 2 decimals. Okay, so any doubt in this question? We first find the linear approximation at the point 1 comma 1. To find it, we need to find the function value first. So function value at the point 1 comma 1 is 17. Then find the partial derivative with respect to x and with respect to y. And what is the partial derivative value at the point 1 comma 1? So these are 9 and 8. Then linear approximation is given as function value plus partial derivative with respect to x times x minus 1, partial derivative with respect to y times y minus 1, 17 plus 9x minus 9 plus 8y minus 8. We got linear approximation as 9x plus 8y. We use this to compute 1.1, 0.9 of the approximation. So we got, let's put x equal to 1.1 and y equal to 0.9. We got this 17.1, and we calculate function value at the point 1, 1 and 0.9. Let's put x equal to 1.1 and y equal to 0.9. So you'll get this. Okay. In question, it is asking you to compute the difference of these two. So that will be approximate 0.13. Any doubt in this question? Then
Sir,
this is it. Yeah, this is it for today. Any doubt in the 10 questions that we solved today? All the 10 questions, or any concept in week 10? No? Okay.
Sir, can
sir,
you just go to
Yeah.
the question number 9? Sir, the definition says the direction of steepest ascent, we need to find the unit vector, right? Delta f divided by the modulus of, sorry, the norm of the delta f, right?
Uh, okay, just a second. I will share one thing. Week 10. Okay. This is in week 10, right? Steepest descent. Okay.
Yes, sir.
Okay. Yeah. So, are you able to see my screen?
No.
Uh, the portal is not
no, sir.
visible.
Yes, sir. Visible, sir.
Now it is.
Yeah. Okay. So now let's read this line. Okay. Uh, gradient continues. Okay. Last line, if we did, if gradient of function f exists and is continuous in an open ball around the point a1 a2 till a10, then the maximum value among all the directional derivatives occur at this point. Okay. So this is what we are calculating here, is the maximum value. Okay. That is the norm of the gradient. Okay. While in the question, they are asking you to find the direction. Okay.
Sir, can
For
you
that,
go down? This one itself, the second question. Can you go down below?
hmm,
Yeah.
this third or second? Which question?
Here, any one of the question here. Here you are finding the um, divided by the
Direct.
modulus. We are finding it, right? The direction only is asked, but we are asked. We were
Find the
finding
direction
the.
which. Okay, what we are doing here? 6x square. It's just check 6x square.
Here the third for the third question. The last option is the correct one, which is the division of the del f
Dividing by.
divided by that norm of that.
Okay.
That is one thing
That
here.
is
we get the direction. It may be a
Direction they
vector.
are unit vector they are taking. The direction
Yes.
for the direction they are taking the unit vector. Okay. So in the question, this is not as the unit vector. 1/2. Okay. 1/8. Okay. Yeah, that is correct. That is because they are taking the unit vector for the direction. Okay. But if you see our question, it is already the unit vector. Okay. Like here. Okay. Let me show.
So
Yeah.
if it is already in a unit vector, we don't need to change in it. Uh,
Yeah.
but
Yeah. See, because
that
even if you divide, it would be the same. Okay. So this vector here is basically already the unit vector. Okay. 1/8 plus 3/8 plus 1/2. So if you calculate it, 1 plus 3 plus 4.
Yeah, okay, sir. Okay, sir. Got it. Got it.
Okay. So it's already a unit vector. So that's why we don't need to divide.
Yeah, okay, sir.
But if it is asking direction, then yeah, convert it to unit vector. Okay. If the gradient is not comes out as unit vector, convert it to unit vector because of the direction. If it is asking you for the maximum value, then find the norm. Okay, norm would be the maximum value. Then in that case, the whatever the gradient you get at that point, find the norm of that only. Don't divide by norm. Okay. So yeah, that's it. Any more doubt?
Sir, will you be taking any activity questions?
Not. If you have any doubt, then that I can take. But for today, I will not take any more question from my side. If you have any doubt, that can I take.
Sir, many a times in definitions there is written open wall. I understand what is
Yeah.
open wall, but why that condition is necessary?
Okay. That because see, in our single variable case, we there were only two directions, left hand side and right hand side, right? To find the limit, what we do, we check the limit at left hand side and right hand side because in that case we have only two directions, uh, right? Okay.
Yes, sir.
So, okay. In that any function, if we have, okay, then we have, if you're finding the limit at any point, we have only two directions, left hand side and right hand side. So we just simply calculate the limit of the function x approaching to left hand side, and if it comes out the limit of the function, let's say x approaching to right hand side, then we say limit exists at the point a. Okay. And the same thing we check for the like the derivative case in the single variable. Okay, same thing, that if left hand side and right hand side are same, directions are same. Okay. In multivariable case, there are not two directions, there are multi, you can say infinite ways from which you can approach one point. Okay. In all which, we if we are, let's say you are taking the derivative, that is the rate of change of a function at a point. Okay. So you see how my function would change, okay, around that particular point. Okay. Whatever the change of the function will happen. Okay. If you're finding, let's say, linear approximation for a function, okay, how my function would behave as a linear, okay, around that point area. Okay. Around the area of that point. So as in multivariable case, we have more than two directions. Okay. Okay, like in 3D. Okay, there are like multiple ways from which you can come to one point. Okay, you can come to any point, like you can go through the straight line, any plane, right? Any plane, any function that can cover that point. Okay, from that direction you can come to that point. Okay, so as there are multiple direction, more than two directions, okay, we consider this as an open ball. Right. Okay, got it?
Okay, sir. Yes, sir.
Yeah. So any more doubt?
No, sir.
Okay, so that's it for today. Good night, everyone. Thanks for joining.
Bye,
Thank you,
sir.
sir.
Thank you.
Good night.
Good night.
Thank you, sir.
Most welcome. The session is recorded. You will get the recording